Hi, I'm Sam Boyer, and I'm going to be talking to you today about Schemata, a new queue-based system for writing evolvable general-purpose schemas. And with the very first sentence of this talk, I've already raised at least two reasonable questions. Why on earth do we need yet another schema system, and why write it in Q? These are very reasonable questions, and the answers are intimately linked, as we'll see. To get there, I want to do some quick definitions and then talk about the problem that we're trying to solve. So the definition that makes the most sense to start with is schema, a specification of the shape of some data independent of the data itself. There are a few different kinds of things we can call schema, but this definition covers them all well enough. Really what matters is that we're talking about a contract between systems that are communicating. Now, modern schema may lend structure to a number of different kinds of things, certainly persistent configuration objects, what we've seen in as code as the state, the files that we have on disk, the DevOps tools that we have for actually doing things with that state on disk, things like protobuf, thrift, data serialization, transmission and validation, data storage, defining SQL tables or querying them, GraphQL, or even programming language APIs. I mean, all of these are forms of schematized contracts. All right. To get into this, we're going to tell a story. The tragedy of the that. Yeah, it's a very simple example of schema usage. I'm just going to center on the schema, capital S, a data object that's an instance of that schema, little s, the producer of the schema, P, and the consumer of the schema, C. So it's easiest to imagine this as programs communicating over HTTP, though we're not restricted to that. Really, I'm underspecifying intentionally with the goal of encouraging your imagination. So we have our producer program, P. And P has published a schema, S1, that specifies the shape of the object we're focused on. We're going to ignore publishing mechanisms for the whole talk. I found color to be the simplest way of expressing what's going on here. P being the same color as S1 indicates that the code within P, which deals with these S-type objects, is working with types corresponding to the S1 version of the schema, the shared color. Okay, so P also exposes some kind of message receiving mechanism that expects these S objects and expects them to be shaped according to S1 by color. Again, HTTP is the easiest to think about. Just imagine this as a path and HTTP API offered up by P. All right, so after some time, P is published, or sometime after P has published its S1 schema, C decides to get it on the game. So the folks behind C ingest S1 and start working with it inside of their program. They get to the point where they're ready to start sending messages, HTTP requests, whatever, to P that are valid instances of S according to the specifications set forth in S1. And for a time, things are good. But then misfortune strikes. The folks behind P make breaking changes to the schema for S, publishing S2. They update their endpoint and the internal logic of P to operate on this newer version. Now, this is the point where the Hacker News discussion devolves. Like, should P have made the change at all? Did they give adequate public notice? Had C done sufficient defensive coding to protect against what every responsibly cynical edgelord knew would happen from day one? Who is the villain in this story? This discussion is at best useless and more often actively harmful. C's broken. At this point, the only thing to be done is for C to update. And everything works again after C's folks do the mad dash. Once the dust settles, a conversation amongst C's people will ensue. How do we prevent this from happening again? And for the most part, even that conversation is useless because the time to address this problem was before the problem happened. That is, what needed to happen was coordination. These folks needed to be aware that the change was coming and change the behavior of their software to accommodate it before P deployed the change to the world. Actually, I need to say this again, but more properly. Coordination. There we go. Much better. So if this set off alarm bells for you, that was the goal. Coordination is the dominant factor that inhibits system scalability. And yes, I'm just going to assert that and move on. The best way to deal with coordination is to avoid it. Find a way to phrase the problem at hand that removes the need for coordination between your systems. coordination avoidance is the entire basis for distributed data systems like CRDTs. So in our example, there are 3 components that need to be coordinated. We have the published schema, and the boundary between the systems contractually joined by the schema, and then the internal structure and behavior of those systems. Depending on the medium, this may be temporal coordination, like if C and P are HTTP servers need to agree on schema at the same time, or maybe logical coordination, where assembling a program from parts or subpackages, and those parts have to agree on what all the contracts are on the components. So if our goal is to avoid the need for coordination in the first place, then certainly in the temporal case, but even in the logical case, there really isn't that much that C, the consumer, can do. C having a problem means that the coordination need exists, which is what we're trying to avoid. So we focus dependency side on the schema producer, P. In general, people offer up 3 strategies for coordination avoidance. In fact, as we'll see, they're really just flavors of the same thing. The first is mostly harmful non-advice, posing as wisdom, but it's worth mentioning because of how often it appears. Just don't make breaking changes. It may have at least flickered in your mind a few slides back when P so ruthlessly moved from S1 to S2, and that's okay, it does for everyone. There are 1,000 reasons this is often realistically just infeasible. I'm not going to dive into them. Instead, I'm just going to offer that a firm premise of this talk and Schemata's design is that engineers would usually like to avoid breaking their dependers, but it's often a relatively low priority on a long list of things, and also high difficulty due to the often poorly articulated rules around what compatibility even means. How do you check it? How do you do that work? That's why putting structure around the problem is key. We have to make it straightforward. Either way, this is a seductively easy premise, one I encourage everyone to guard their minds against falling prey to. Okay, so real strategies. The next more actually real advice is to make an externally versioned API. That is, inject an explicit version numbering component into whatever passes for the address that receives messages in the system at hand. Now, if you really honing on that HTTP API interpretation of our tragedy case, then we're thinking about HTTP endpoints. So the convention here is to add a prefix component at the root of the path. Then we're sending S1 to the existing /S path, and the new form, the v2 can go to /v2/s, and everything's fine. Now, of course, there's the question of how P's internal behavior supports the S1 form of the S instances at the old endpoint, since it internally wants to work with S2. We'll come back to that. The third approach is to accept both old and new inputs. This, by the way, is what you're actually saying when you say just don't make breaking changes. That is, A makes the breaking change non-breaking by hiding it inside some abstractions within A's internal behavior. We want our endpoint to take care of the nasty business of making sure that by the time we're in the main body of P, it's an S2 instance, whatever form it arrived in. And really, that's given away the whole game. We want the program boundary to be where all this translation occurs, so that it doesn't need to bleed into the rest of our program. Because without clear patterns to follow, clear rules, it is astonishingly easy to end up in this situation. An unencapsulated endpoint leads to a messy P with a complexity of needing to consider that multiple versions of S exist sprawls throughout the codebase. And C isn't immune either. Once updated, it's perfectly plausible that it could emit a valid S2 instance, even if it's tripping up internally over which version it's using. In fact, this almost seems more likely to me if the C folks are feeling the need to code defensively after being burned. There's prior art to doing all this. And it should at the very least leave little doubt as to the utility and viability of designing systems around a pattern that tries to isolate translation at the boundary. Kubernetes itself has mechanisms for this, CRDs and webhook conversions. It's the right functional pieces, though they're quite loosely coupled. Now, famously, Stripe's HTTP API has been versioned since forever and a half. It still accepts all old input forms. Clearly, one can build a successful company around strategies like this, or even arguably because of strategies like this. Project Cambria, which someone actually pointed me to after we had the basics in place with Schemata, is the closest thing to Schemata. A generalized generic attempt at encapsulating the problem of schema evolution. It's very cool what they've done. I'm going to reference them a couple more times later. But we've got a pretty good problem definition and goal definition, but I really want to drive home what the goal is with Schemata. For that, I'm going to pull a term from the discussion that sprung up around domain-driven design. So an architectural quantum is an independently deployable component with high functional cohesion, which includes all the structural elements required for the system to function properly. This is from the book, Building Evolutionary Architectures. The goal of Schemata is essentially to be this for this problem space. That is, we hope Schemata can be the quantum of schema. One of the fringe benefits of being a dad is the license it gives me to make literally Comic Sans level of badness dad jokes with absolutely no guilt hangover. In saying that Schemata is the quantum of schema, I'm making the argument that schema evolution is a necessary part of every system in which schema are used as contracts, shared contracts. That's because if we consider system to include all our coupled coordinated parts from earlier in our story, then it's clear that deploying schema without proper provisions made for evolving them means that the system will fail that crucial functioning properly criteria. All right, let's talk about what schemata actually are. Now, please note some of these names are still subject to change, but the concepts they represent and the invariants that come along are fixed, even if some are a little untested and aspirational. All right, the main pieces. Schema, we've talked about. A lineage is a sequence of backwards compatible schema. A lens, mappings between schema. Lacuna is a gap in translation, and a family is all the things together. But let's explain them visually, because that makes it make more sense. So the overall family, well, in our early example, we had 2 schema. We're now going to say that there are 4 schema because it's going to help us describe some important properties of schemata. So let's say this family contains 4 schema. These are split into lineages, which are backwards compatible sequences of schema. That means that O.1 is backwards compatible with O.0, and 1.0 is backwards incompatible with O.1. Here we're relying on Q's native definition of backwards compatibility, which there are some quirks around, but too much detail for this talk. Then we have lenses. Lenses are mappings between schemas. Within a lineage, lenses are implicit. The schemata author need not define them because that's pretty much what it means to be backwards compatible. Old versions work cleanly as the new version. Now, it's not so straightforward for reverse lenses within a lineage. They can't just be implicit. I only firmly decided to add reverse lenses in the last few weeks, so I'm still figuring out how to work these into the design. I'm just going to skip over it for now. The other 2 concepts, lacuna and translations, are things that we see when actually using schemata, which we'll look at next. But let's look at the key invariants real quick. So all these are checkable schemata invariants. Families must contain at least one lineage, and lineages must contain at least one schema, which is really just saying that they can't be empty. There must be this backwards compatibility relationship within lineages, but not across them. And then each lineage beyond the first must define a lens to and from its first schema. This is really just the lenses back and forth across lineages. These are the essential invariants. All right, I've got one last one, which I've italicized because I literally just realized the necessity of it. Yes, this is where this project is at in its phases of evolution. I don't want to talk about it. I just want to avoid anybody who realizes there's a code smell here, like going down this path and feeling the need to write up thousands of words explaining this. So let's look at what it takes to actually use schemata. That's going to tell us more about translation and lacunae. We have our lineages of schema linked by lenses. These are the structure we're operating over, so I'm going to keep them in the visual, but what we're going to focus on now is actual concrete resource passing through the structure as it gets translated. So we're going to de-emphasize them. We have our program. It has an instance of S00. We'll take this as a given that the program has already used the schemata to verify this object through validation. It is a valid instance of schema 00. So parts of the API exposed by Schemata is a call to translate an object. This currently exists in Go and kind of in Q, but this is what needs to be exposed in a programming language in order to make the whole Schemata system usable from that language, which means you need a Q evaluator as well. The translate call takes a valid object and a destination version to which the object should be translated. Here, the destination and starting point are the same for S0.0. That makes this call basically a no-op. But the action starts when we start asking to translate to 0.1. That means we're passing S through a lens. This one implicit because we are within a lineage. This pass-through produces the translated version of S, which will include changing a version number field from 00 to 01 within S itself, applying any defaults. There's also a second value that comes back from the translate call. That's a set of lacunae. Now, in this case, we can know that that set is empty because being backwards compatible is equivalent to saying no gaps are possible in this translation, and therefore no lacunae. Now, note that the representation of the S instance on both way in and out is a pass-through to what the Q evaluator API can accept and produce. It's easy enough to think of it as just JSON bytes, not native types. That's a separate thing, native language types. Okay, next we go 2 steps in one translation, crossing to 1.L. It's the same inputs and outputs as before, but now we're passing through an explicit lens, one written by the Schemata author that allows S to traverse the break and change. The lacunae from previous translation steps, there aren't any, but they're accumulated together with any emitted by this step. And indeed, being break and change, some may be emitted. And indeed, this is an essential point about the design of Schemata. It is not possible for this step to fail. Lenses must produce a valid translated object, even if it means filling in some kind of placeholder value. Lacunae are the means by which Schemata expresses some basis for failure. It's the program's responsibility, though, to make that decision, not something based in the Schemata itself. That means no program can be forced to abort translation. This effectively makes hard errors into soft errors, which is essential to reliably relieving the coordination way back out in actual running programs land. All right, finally, we take the object all the way through to the latest schema. Again, the lacunae accumulate, but no more could possibly be added in this step because it's a translation through an implicit lens again. So one of the things to note, we're saying nothing at all about persistence. That's also about design. It's clearly up to the calling program to decide whether and how to persist a translation. All this is stateless, what's happening here. Leaving that up to the program is a key part of making Schemata as broadly useful as possible, just like making it impossible to fail on forward translations. All right, we've got a general sense about translation and lacunae work and what the invariants are. What does it all add up to? A program can always translate a valid object to the latest schema version. Lacunae are sufficient basis for programs to handle all possible remediations that they might need to run. Schemata encapsulate all the logic necessary in this append-only immutable data structure that is ripe for publishing and consuming. And ultimately, what we want, systems communicating through schematized contracts can, within limits, safely evolve without coordination. Evolutionary decoupling, our goal. Now, on this last bit, the within limits bit, I want to read something from the Project Cambria folks, whom I think put this rather aptly. With a flexible schema evolution system, compatibility becomes more of a human-centered design question. How far can 2 pieces of software diverge before it becomes impossible to usefully collaborate between them? Lens evolution cannot magically make 2 incompatible pieces of software work perfectly together. The goal is merely to enable developers to maximize compatibility within realistic limits. They're absolutely right. This is not a panacea. It's not magic. But it gives us the framework for being able to express these relationships and compartmentalize the problem into a small space. All right, we've talked invariants, we talked use pattern from a program, but as I noted earlier, the premise of this whole design is that people would deal with compatibility only if it were easy enough. Part of that is getting the invariants right, but the other part is making it ergonomic enough that people can intuit what's going on, trust the system that they're working with. Schemata, still being in its early stages, like Q itself, certainly has rough edges, and we're working on improving those. But I set up a goal from the outset that it'd be possible, and indeed the default case, that schemata are expressed entirely in a single file in a single data structure. So let's actually look at some real actual schemata. This is about as simple as I can imagine. We import from Grafana schemata, we mark that the whole file is supposed to be a family, and then we have our lineages structure. Lineages are a 2-level nested array. The version number for a schema is derived from its position within this 2-level nested array. That's very important. It means that version numbers, unlike any other version numbering system that I'm aware of, have a direct checked correspondence to backwards compatibility relationships. They mean something machine verifiable in a way that almost no other system does. Elm's package management would be the exception. So our 0.0 version of schema defines some field, which is a string, and then the 0.1 version just adds another field, an optional one, and composes in the prior schema. This is likely something that will it's an edge to be sanded off, right? Like there's a lot of boilerplate to be removed. So this is a basic schemata because we're not doing any lenses. Let's look at some lenses. So same basic pattern up top, import, set the whole file. But now we're going to have two lineages. Our first one, schema 00, we have a boolish. This is kind of YAML-ish in the way that YAML has these fun, stringy, truthy, falsy values. And what we're going to model here is translating those into proper bools. This isn't this is a toy problem. Q already has things built in to be able to do this, but it's nicely illustrative of the way that we need to think about writing lenses. So we have our two schema 0010, and we want to define our lenses between them. So lineages beyond the first must define lenses. And first, we're going to do our forward lens. This defines the translation from the end of the prior lineage, lineage 0, to the beginning of the one that we're in this declaration, which is lineage 1. So this is all boilerplate, but basically which schema we're mapping to, which schema we're mapping from, and then out is where we collect a return value on the other side. Again, hopefully boilerplate stuff that can be removed as we improve the schemata as a framework. Rel is where the actual mapping logic is, though. And what we're opting to do here is we see if the input boolish is a string, then we check and see if it is exactly equal to true. And if it's not, then it ends up being false, meaning that the true case is true, the false case is false, and any other case is also false, since original input allows just a string. The secondary thing is just the simple, oh, it actually is a Boolean case. Okay, just assign it directly onto proper bool. Q and I is where we specify our gaps in translation, and this is probably the most interesting feature. So I picked something that I hope would be indicative. They're also quite underdeveloped. We haven't had to actually do any of these yet in Grafana land. So we're only going to middle the QNA if the translated object actually had one of those weird string values. So we want to see if it's a string, and if that string is neither true nor false, then we will add a lacuna to the overall list of lacunae. The actual definition for lacuna is in flux, but here we're recording the path that was a problem, the value, and then there's going to be some kind of taxonomy. Because this is essential. If we did not have a well-founded taxonomy for the classes of lacuna that are omitted, it would be realistically not possible for any program that uses Schemata to actually be able to make good decisions about what to do when lacunae are omitted. You'd just be string sniffing, and you'd be back to string sniffing and errors and less happy language days. The reverse translation is much simpler. It's the same kind of thing, just the mapping in the reverse direction. But here, we're just saying the proper bool goes directly to boolish, very clearly establishing that it is a non-goal of Schemata that preserving the exact original input is what we're trying to do. It's not what we're trying to do at all. So just quickly, some test cases. It's hard to actually show these running, so I just have some output, but inputs of Boolean true, string weird, string true, string false. So when input is Boolean true, true and true when we go forward and back. When input is string weird, forward val translates it to false, as we would expect, which ends up coming back to false, but we crucially have the lacunae record indicating that it was weird, so that the surrounding program can take action if it wants. And then string true and string false translate to true and false, as we would expect. Okay. So returning to the original question, why get another schema system and why Q, right? Schemata is providing this framework, this architectural quantum that includes breaking changes and encapsulates these structural elements in a single logical structure. Q makes it possible to define. I can't really imagine writing this in another language, frankly. The structures that we need to be able to capture these minimum necessary elements in order to have a system like this. Q is also amenable to translation into the many languages and contexts that schema need to govern, which is key. This needs to be widely usable, and being able to translate it, especially if there isn't an evaluator written in that language yet, is essential. This is one of the things we're doing at Grafana in using Schemata. Is we are, instead of trying to get a TypeScript evaluator written, I just wrote a TypeScript translator for Q, and we translate the most recent version of Schema. In that vein, let's talk about some of the implications. We have our basic understanding of what Schemata looks like. So let's look at what it looks like to develop programs when we have these kinds of structures in place. We'll pick up our original tragedy of the pixies. So when we last saw our heroes, they'd been overcome with the creeping complexity of multi-version schema seeping into all parts of their programs. Now, if P publishes changes with Schemata, the potential for complexity creep is drastically reduced. P has everything it needs to contain schema translation at the boundary. It almost has to try to let it bleed throughout the entire program. What may be a bit surprising, though, is how C's experience of working with schema changes as well. Let's imagine C is back before they spewed schema all over the place, right? We're back here. Now, P has already solved the coordination / breaking change problem for C and all other C's like it, right? So it's at least acceptable for C to keep on using its old version of S, keep on sending that to P. But once translation logic is encapsulated into Schemata and published, C and P have symmetric capabilities with respect to how they handle translation, limited only by the availability of a Q evaluator in their respective languages. This opens up new degrees of freedom on C's side. C can check over the lacunae emitted entirely on their own side without ever having to send an HTTP request or anything, interact with P at all directly, whatever the form, and form their strategy accordingly. Maybe it's perfectly fine for C to keep their code base as is, or maybe it's not, and they should move to later versions, but they're much less dependent on P to actually find out. This gets especially interesting when we focus on infra as code type cases. Now, I know I'm really stretching the visual metaphor here. We're almost done. Just stay with me. It's not uncommon for infra as code tools to have relatively weak opinions about the objects they deal with. They're pass-throughs, at least to some extent. Their job is to manifest a mapping between a particular arrangement of files on disk and some running systems that know what to actually do with those files. kubectl is a good example here. It can't actually validate objects on its own, really. It relies on the Kubernetes API server instead. Translation is also locked up within the API server because it tends to rely on webhook calls out to operators, which can make translating these object files sitting on disk a bit awkward. But if kubectl or whatever tool's knowledge of schema could, by design, include and supersede whatever active versions of objects exist within a particular Kubernetes server, this would drastically shorten the length and complexity of the validation and translation feedback loops. kubectl can do things on its own in accordance with what an API server would do, but any API server, not just the one that it's currently talking to. It doesn't have to be beholden to it in quite the same way. It can send known objects. It can validate the objects on disk. It can do the translations of them. Going one step further, we have a roughly similar setup around Grafana with the tool Tonka. Here, imagine the files represent the heaping complexity of Grafana dashboard JSON. Among other things, Tonka will deploy this out to a Grafana instance. Along the way, we can take an additional step, lint queries. Grafana dashboards usually contain a lot of query strings that are opaque, at least at the level of schema. We could write a query linting tool that checked some queries for some properties. And even if that tool stayed focused on old versions of Grafana dashboards, as long as it checked the lacunae of dashboards passed to it for validation, for any indication of change to the expected query pass, it would be able to offer true positives, passes, and its linting checks essentially in perpetuity, despite being dependent on the old version. What we're looking at here is a realistic case with heterogeneous object version inputs into a network of communicating programs, all of which are operating on objects at different versions or don't know or care about them effectively. It is the height of distributed evolutionary independence. All right, there's a ton going on in this whole system. There's a bunch that I didn't have time for. Object headers, composition, which is a thing that we're doing in Grafana right now because we have to, because Grafana is a pluggable system and has pluggable schema. What do you do in development? How do you actually manage publishing? How do you map things into families? These are all great questions, and this is not by any means a complete list, but I wanted to at least put some of them up here to assuage concerns. That is all that I have. Thank you very much. This is where the repository either is or will be soon. Thank you.